In this lesson, we're going to look at conditional probability, and we're going to do a lot of examples.
Okay, hi everybody. So in this lesson we're going to take a look at conditional probability. And what we're talking about here are events where, let's say, the first event changes the sample space and alters the probability of the second event occurring. Okay, so there's some dependence here. Okay, the second event really depends on the first event. Okay, and how you calculate the probabilities is going to be reflective of that. So let's take a quick look at an example, and then we'll go through a little bit of theory before we do some questions. So the table below shows the results of a survey which compares compares eye color and eyesight for 125 adults, and the table is incomplete. So we got to fill this in here. So that's going to be fairly common here. So going down here for blue eyes here, we've got 31 and 26. So together that's going to be 57 people. We look at brown eyes here. We've got a total of 68 people here, but we've got 55 whose eyesight is good. So that leaves us 13 whose eyesight is going to be bad. And then we just go through and do the totals this way, okay, just to double check that we're doing this right here. 26 and 13, does that give us 39? Yes, it does. 31 and 55 is going to give us 86. 57 and 68 here, okay. Well, let's see, that 5 and that 7 are going to be a 15. Going to add, it's going to be 125. Now, does that work if I go down this way? 6 and 9, 15, carry those, 125. Good. So we know that we filled that in correctly. So now, let's take a quick look here. So find the probability that a randomly selected person is blue-eyed. Okay, so what we want here is the probability that someone has blue eyes. Well, I've got 125 people total. And how many of them have blue eyes? Well, 57. So there it is. 57 people out of 125 have blue eyes. Done. Let's look at the next one. Find the probability that a randomly selected blue-eyed person has bad eyesight. Okay, now this is interesting here because what we've done is we've narrowed your focus to one group of one small subset of this larger universe here. Find the probability that a randomly selected blue-eyed person. So in other words, what's going to happen here is I already know, going back up to my chart here, that I'm not worried about that right there. Okay? So we're going to see in a little bit that what we can do here is we can use this probability of finding a blue-eyed person to help us get the specific probability that we're looking for. But for right now, we've got enough information that we don't need to do that. I'm just going to ignore everybody else. I'm only concerned about the total number of blue-eyed people and how many of those have bad eyesight. And that's going to be 26. So how I write that is I want the probability of, let's say, bad eyesight, and I'm going to draw this vertical line here. And that vertical line is going to mean given that. Okay? So this right here is going to be given that, and I've got this little arrow here, and I know it looks terrible, but anyway. So what is the probability that someone has bad eyesight given that they have blue eyes? And in this case right here, we knew that there were 26, because I saw that in my chart here, there's 26 out of 57 people in that group. Hope that makes sense there. Find the probability that a randomly selected person has bad eyesight. Okay, well that is a more general thing again. I'm just asking, what is the probability that someone's got bad eyesight? Well, I know that there are 125 people here total. So now I just look at my total here, and if I look across to bad eyesight, there are 39. Okay? So 39 out of 125 people have got bad eyesight. Let's go one step further here. Find the probability that a randomly selected person with bad eyesight has brown eyes. Now, in this case right here, notice that what I've done is I've now focused my attention on that subset of the population with bad eyesight. Okay? That's the only group I'm looking at. So if I go back up to my chart here, I'm now only looking at that group of people represented right there. And here's the brown column. So the way I write this is going to be the probability that someone has brown eyes given that they've got bad eyesight. Okay? And that is going to be, okay, we look up here, how many people have bad eyesight? 39. Now, sorry, yeah, and how many of them have brown eyes? How many of those have brown eyes? It's going to be 13. And I get 13 out of 39, or 1/3, okay? Now, just a little thing before we go on here, okay, before we carry on with this, I want to go back up to this question right here just for a moment. I want to switch those. Just for fun here. Let's do this. What is the probability that someone has blue eyes given that they've got bad eyesight? I want you to notice something about this. Okay, in that case right here, again, just like I did that last question, I am only looking at that second row, so just that group of 39 people. And now I'm interested in the group of people that have blue eyes here. It's 26 out of 39 here. So that's 26 out of 39. Now, notice, everybody, that those probabilities are not the same. Okay, they are different. So it does make a difference, okay, which set you're looking at initially. Whether you are looking at the set of blue-eyed people first, or you're looking at the set of people with bad eyesight. That does make a difference in the probabilities at the end. And it's very important to notice that when you switch that, it does change the probability. A very common mistake that people make is to assume that it doesn't matter what order those go in. In fact, there's all sorts of examples of people doing goofy things because they assumed that those probabilities were the same. Okay, so now that we've walked through that, just a little bit of kind of theory here. So if A and B are events from a trial, the conditional probability of A given B, okay, so A given B, is written as the probability of A and that vertical line B. So A given B. So we know that B has occurred. We've accepted the fact that B has occurred. We're now looking inside the B set. Okay, if you want to think of it like as a Venn diagram, I'm looking inside B, and we want to know what's the probability in that context that A is going to occur. So, and the way we might do that in terms of our formula here is what we're going to do here is we're going to find the probability of event A intersection B divided by the probability of B. Now, if I could just draw the Venn diagram here. So here's A, here's B. Basically what we're saying here is, look, we're assuming that B has occurred. Okay, then I'm just focusing my attention on that. So this is, I'm basically reducing my focus here to just this. So my population, or my universe, has now become just the set B. And what I'm interested in is where A occurs as well. So it's that little bit right there. So I'm interested in that probability, okay? This amount over this total amount. And that's what we're seeing reflected right here in this equation. Now, a couple of things that you should know about that. Okay, so in an experiment, two events are independent. Okay, independent if the probability that each event will occur is not affected by the occurrence of the other event. Okay, so if one event has no impact on the other, then they're independent. So think about it like you're spinning a spinner or rolling a die. Okay, they don't affect each other. There's no interaction there at all. Dependent events, on the other hand, are events that are, and get this, not independent. Okay? Now, typically what that means, what dependent events means, is that one event kind of affects the other one. There is a relationship there. Although I've been told by those that know way more about this than I do that that's maybe not the best way to understand it. The best way to understand it is that it's simply not independent. But for our purposes, to get across the ideas that we want to get across, it really does help to think that the one event influences the probability of the other event, okay? So it's like having a deck of cards and you pull a card out. If you don't put that card back into the deck, you have changed the probability that another card gets pulled, okay? Because you've changed the size of the sample space. Now, two events A and B are independent, okay? So, if they are independent, then the probability of A given B is just the probability of A. If there's no impact, okay, if there's no influence there, B doesn't do anything, then the probability of A given B is just the probability of A. The probability of B given A is just the probability of B. Okay, same thing going on here. And here's probably the more significant result. Want to make sure that you've got this one. The probability of A intersection B, okay, where the two happen together, is going to be equal to the product of those probabilities. Okay, I'm going to multiply those together. So here's where we're really getting a good idea of and means multiplication. Now in a previous lesson you would have seen or, and you would have seen us use a lot of addition and a little bit of subtraction there just to balance things out here, but you would have seen the addition in there. So now we're seeing the other side of that, the and becoming multiplication. Okay, now let's take a look at some questions. Okay, so our first question here is going to be classify events as independent or dependent. Okay, so the trial is flipping a coin and drawing a card from a deck of 52 cards. The first event is rolling a heads and the second event is drawing an ace. Well, does that first flipping of the coin affect the drawing of the ace? Not at all. Independent. The trial is rolling a red and a green die. Okay. The first event is rolling an even number on the red die, and the second event is rolling a 6 on the green die. Okay, well, does rolling a value on one die have any impact on what's rolled on another die? The answer is no. Independent. The trial is to sample two members of a family, a mother and her child. The first event is that the mother has brown eyes, and the second is that the child has brown eyes. Okay, well, now, does the eye color of a parent affect the eye color of the child? Yes, it does. Those are dependent. Okay? So that's totally dependent. Next. The trial is drawing 2 marbles from a bag containing 3 red, 5 white, and 2 blue marbles, replacing the first marble before the second marble is drawn. The first event is that the first marble is red, and the second event is that the second marble is white. Okay, if you put that marble back in, you've reset the sample space. So that first event really has had no impact on the probability of the second event. Okay, in fact, basically I can do these in either order. It doesn't make any difference because the sample space is reset. So these are going to be independent. Now look at this last one here. The trial is drawing 2 marbles from a bag containing 3 red, 5 white, 2. So it's the same situation. But this time we're not replacing the first marble before the second is drawn. Okay, so when you take that marble and put it out, the number of marbles in the bag has now dropped by 1. I've changed the sample space. I've changed subsequent probabilities. So yeah, these are going to be dependent. Subsequent probabilities are going to depend on that first event occurring. Okay, and so it should give you a bit of an idea of what we mean by independent and dependent. Okay, here we go. So a card is drawn at random from a deck of 52 cards, and a fair die is rolled. Find the probability that the card drawn is a spade. Okay, so we've got spade, and the die rolled is a 3. So we want the probability of a spade and a 3. Now, are these dependent or independent events? Does the card drawn affect what the die is going to be? And the answer is no. No, it doesn't. So these are going to be independent events, which means to get their combined probability here, the and probability, I have to multiply their individual probabilities. Okay, well, what's the probability of getting a spade? Well, there are 13 spades out of 52 cards. That's 1/4 of the deck is spades. When rolling a 3, there are 6 possibilities, so that only one of them is a 3, so it's going to be 1/3. When I multiply those together, I get 1/12. So that's the probability of rolling a spade. Sorry, rolling a 3 and drawing a spade. Okay, so now, again, it says find the probability that the 2 cards are hearts. So what we're wanting here is what is the probability that the first card is a heart and the second card is a heart. Now, typically what we would do in a situation like this, if these were independent events, is we would simply multiply the 2 probabilities together. Okay? The thing is, though, we've already established these are not independent events. They are dependent. So what we're going to do here is we're going to take the probability that the first card is a heart, and we're going to multiply it not by the probability that the second card is a heart, but by the probability that the second card is a heart given that the first card was a heart. Okay? So it's a little bit more complicated right here. I have to take into account the condition that was met by this first event, because it does change the probability here. So now, what's the probability that the first card is a heart? Well, the first card being a heart is going to be 13 out of 52, or 1/4 if I want to think of it that way, okay? Because I can reduce to 1/4 here. Now, I could use the formula to figure out what the probability of the second card being a heart, given that the first card is a heart. I could do that. That's not actually necessary here. I just want you to understand how dependent probability here works, because you've already got a good sense of what's going on here. That formula is really useful when it's maybe not as clear how that relationship works. But here I already know what happened. I'm already aware of what's going on. That first heart being pulled out has reduced my denominator to 51. Okay, simply because I've taken that one card out, and assuming that that first card was in fact a heart, and when you're dealing with probability, you always assume success there. There are now only 12 hearts to work with at the end. Okay, so now what I've got here is 13 times 12 here. It's going to be 156, and then 52 times 51. It's going to be 2652. And then let's just simplify that, 2652. I'm just going to let the calculator do this because I'm too lazy. And so this is actually going to work out really nicely, just become 1 out of 17. Okay? So there it is. There's the probability. It's a 1/17th probability that the second card is a heart, given that the first card is a heart. Oh, sorry. And then that, in addition to that, that the first card was also a heart. Yeah. So I have to have all those probabilities together. Okay. Now this question here is going to read very similar to that previous question. Okay. 2 cards are randomly drawn from a deck of 52 cards without replacing the first card before the second is drawn. Find the probability that the second card is a heart, given that the first card is a heart. So that should sound a lot like that previous question here. The difference is I'm not asking you for the probability of both events. In this case here, I'm just asking you for the probability of that second event. What is the probability that the second card is a heart, given that the first card is a heart? That's all that I want. In that previous question, the question was, what is the probability that the 2 cards are both hearts? So I have to include the probability of the first card being a heart together with the probability that the second card is a heart, given that the first card was a heart. I know it's a little confusing here. But here we go. In this case, this is a little bit of a simpler scenario here. I simply want to know how that first event, and I'm assuming that it happened, okay? I'm not determining the probability that it's going to happen. I'm assuming that it happened. So as soon as that first card is drawn, I know that there's only 51 cards left in the deck. And because that was a heart, I know that there's only 12 cards left. And so that's what I want to determine here. A little bit easier problem because it's not including the probability of that first event. Okay, so in this question here, we read, given that the probability of A is 2/5 and the probability of A and B is 1/3, find the probability of B given that A has occurred. Okay, so what that is going to be is the probability of A intersection B over the probability of A. So that's what the formula is telling us to do. So that denominator there focuses our attention on just that A set, and here we're looking at the A intersect B here. Now I know that A intersect B is going to be 1/3, and I know that the probability of A is going to be 2/5. So that's 1/3 multiplied by 5 halves, or 5/6. So that's the probability that event B happens, given that event A has already happened. Now let's take a look here. If the probability of A given B is 7/8, find the probability of B. Well, let's take a look at that. So the probability of A given B is going to be, again, the probability of A intersection B all over. This time it's going to be the probability of B. Now, in this case, I know what this number is, and I know what the intersection is. So what I'm going to do is I'm going to multiply through by the probability of B. So it's going to be the probability of B multiplied by the probability of A, given that B has occurred, is the intersection. And now the probability of B is going to be that intersection divided by the conditional probability of A given B has occurred. Okay? Now, I already know that the intersection was 1/3. And here we're told that that conditional probability is going to be 7/8. So now that's going to be 1/3 multiplied by 8/7, or 8/21. That's the probability that we're looking for. All right. So in this question we read that contingency tables are a useful way to solve conditional probability problems. The contingency table below shows an analysis in terms of gender of students taking a grade 12 mathematics course at a specific school. So we've got Math 31, 30-1, 30-2 in our totals, female, male in our totals here. Okay, so find the probability that a student is taking Math 30-1. Well, first of all, let's take a quick look here and figure out our total is 87. Okay, so the probability that someone is taking Math 30-1, okay, and there's nothing else mentioned here. That's all I'm asking for. So that's going to be out of 87. And now I just have to look at here. How many are taking 30-1? 30. Okay, so 30 out of 87 here. And I'm just going to actually go to my calculator here and let it simplify that for me. Oops. That's going to be, yeah, 10 out of 29. Oh, and there you go. Okay, that's it. How about the probability that a male student is taking Math 30-1. So we want to know that the probability that a male student is taking that particular course. Now in this case, what the information that I'm giving you, the thing that you can assume is that we're talking about a male student. So the thing that I'm making, or I'm looking at the probability of, is whether or not they're taking 30-1. So this is Math 30-1, given that we've got a male student. Okay. So what we're doing in this case is we've got the probability of 30-1 and male over the probability of being a male. So now I can do this differently. And in fact, what I'll do in a couple seconds here is I will do this differently just to illustrate what you could have done here. But the probability of 30-1 and male, okay, 30-1 and male is going to be 13 out of 87. And the probability of being male is going to be 40 out of 87. Now, I'm going to multiply by the reciprocal there, and you should notice right away that those 87s are going to cancel. I'm going to be left with 13 out of 40. Now, the other way to look at that is we are restricting our attention to just the set of males. And I know that there are 40 males there total. So what I'm doing here is I'm covering up everything else. I don't care about the totals. I don't care about the group of females there. I just care about the group of males. And I'm looking for the group that are taking 30-1. So 13 out of that group of 40, which is the result that I got by using my formula. So the next question is, what is the probability that a female student is taking 30-2? It's the same problem here, right? We're doing the same thing. But in this case here, let's move this one along a little bit faster here. So this is going to be, I'm still looking for the probability that that course is being taken. But in this case right here, what I'm given is that I've got a female student. And so now I'm going to sidestep this a little bit. Where is my group of females here? That's right here. And there's 47 total. So right there, I've restricted my attention to that set. And now I'm looking for how many are taking the 30-2. And there's the 23. Okay, so 23 out of 47. Okay, and actually that's as good as that's going to get. That's those are both nice prime numbers there. How about this one? How about what's the probability that a Math 30-2 student is a girl? Now, I've already looked at this sort of a situation earlier here, but here's another spot where it pops up. Notice that what I'm doing here is, in this case, the information that's given is that I've got a 30-2 student. So what I'm looking for is the probability of that student being female, given that they study Math 30-2. So again, without using that somewhat cumbersome formula here, because I don't need to, I've got all the data here. I'm looking at the 30-2 set, right here, 31. There's a total of 31 students. Now, how many of those 31 students are female? And the answer in this case is 23. So 23 out of 31. And again, notice that it does matter. If you change the order of those things along this conditional probability statement, it does make a difference. How about what's the probability that a Math 31 student is a boy? So again, we are assuming the 31 student, and we're looking for male here. So Math 31, my mistake. Okay, Math 31. Oops. Oh boy, now I'm just making a mess. So we're going to let this be the denominator, the set that we're working with. So Math 31, there's my set. There's 26 in that set. How many of them are male? Well, I go up to that set here and I look across to the male. There's 19. So the probability is going to be 19 out of 26. So if you've got that information and it's broken up as nicely as it is here, it's not necessary to use the formula, but the formula will work. Okay, let's keep going. Okay, so in this question right here, I'm going to go about this in a couple of different ways here, again, to try to illustrate the power of both ways of thinking here. In a class of 25 students, 14 like pizza, 16 like coffee. Okay, now one student likes neither, and 6 students like both. Okay, one student is randomly selected from the class. What's the probability that the student likes pizza? Okay, so here we go. Probability that the student likes pizza. Well, that I don't need to really do much in terms of drawing out the set here and whatnot. Now, I am going to use a Venn diagram here in just a moment, but I don't really need it right now. I've been told that 14 like pizza out of a total of 25 students. So there's my probability that that the student likes pizza. 14 out of 25. Nothing complicated about that. So now, let's do this though. What's the probability that somebody likes pizza given that he or she likes coffee? So pizza, given that they like coffee. Well, that is going to be the probability of liking pizza and coffee over the probability of liking coffee. And again, it's this division by this probability of liking coffee that focuses our attention on that one set. Now, this information we are given here, actually. Okay? How many people like pizza and coffee? Well, I was told that 6 do. 6 out of the 25 people that we've got total. Okay, what's the probability of liking coffee? Well, it was 16 out of the total of 25 people. Now, I've got a fraction divided by a fraction. I'm going to multiply by the reciprocal here, and notice that the 25s will cancel, so I'm left with 6 out of 16. Okay, and that can be reduced down to 3 out of 8. And so there's the probability of liking pizza given that you like coffee. Now, let's take a look at what that Venn diagram would look like. 25 students, pizza, coffee. Now remember, I'm given information about the entire set here, and the set of pizza likers, the set of coffee likers, again, that always includes 2 sets here, so I have to be able to start in the middle. I've got 1 student that likes neither, so they're out here. 6 students like both, which means out of the 14 students that like pizza, there's going to be 8 out here. And then for the 16 that like coffee, there's going to be 10 right there. And so now, what's the probability of liking pizza given that you like coffee? Well, what we do is we're focusing your attention on just that coffee set. And how many students are in the subset that like pizza? Well, 6. Out of a total of 16, and that's what we got. Okay, so they work together. They're complementary ways of thinking. Okay, so in this question we read that in a group of 50 students, 50. So I see my Venn diagram right here. I'm going to fill that in, so I'm going to just throw that out there right away. 40 study math, 32 study physics, and each student studies at least one of these subjects. Okay, that's an interesting bit of information because what that means here is we're looking at exhaustive sets. Okay, these two sets cover everybody. Everybody is within these two sets here. So what I've got here is I've got mathematics and I've got physics. Okay, now I'm given information about these two sets and about these two sets, but I'm not given information about any one of those sets. However, just take a look at this. If I take 40 students here and add to that the 32 students here, 40 and 32 sounds like I should have 72 students being considered here. 72 students. I've only got 50 though. Now bear in mind, there's nobody outside of these two sets. So when I added this set to this set, okay, that should have been the total. But it's not, it's too big. Now I guess I kind of expected that because this section right here got doubled. Okay, I got added twice here. So I got 72 as a result. Well, 72 is 22 bigger than it should be. So I already knew that I was going to subtract this bit right here. So this must be the 22. Okay? I mean, think about it. In order to get the full, value here up to 50, okay, what I was going to do is I was going to take only m plus m and p. Okay, so this is m. This is the set m right here. Only m and m plus p. And I was going to take p, which was only p, and m and p. Because m has two sets, p has two sets. If you add those together, okay, then what happened here is the sum is going to be only m plus only p plus 2 times m and p. So what I've got to do here is I've doubled that up. So I was going to subtract one of those already to get down to the total amount of people here. Well, I was 22 too big, so that means the middle portion here must be that piece that I was going to subtract. Now, if that's 22, then I can tell you right now that this part here studying only mathematics must be 18, and this part here studying only physics must be 10. Just by doing a little bit of subtraction here. So now we can answer the rest of this. If a student is chosen from this group randomly, find the probability that he or she studies mathematics but not physics. So studies math and not physics. And again, I can read this right off of the graph here. So studies math and not physics. Well, that's this right here. That is that group of 18 out of that total of 50. And we can simplify that. That's going to be 9 out of 25. Or how about studies physics given that he or she studies mathematics? Okay, so studies physics given that he or she studies mathematics. Now, so now we're focusing on just the math set. There are 40 people here, and there are 22 out of that 40 that study physics. So 22 out of the 40, or 22 out of 40 is going to be our probability. Divide that by 2, we're going to get 11 out of 20. Okay, because remember, when I say given that, I'm narrowing my focus. Instead of it being this full universe, I narrow my focus to just that set of mathematics students. Okay, let's take a look at this question here. It says, in a class of 40 students, 23 have dark hair, 18 have brown eyes, and 26 have dark hair, brown eyes, or both. It's like, oh, okay. Well, now when I read that right there, what I'm reading is a kind of a union of two sets. One, the other, or both. Okay, that's the union here. So now a child is selected at random. Determine the probability that the child has, and we've got some ideas here. Okay, well, let's take a look at the Venn diagram here first. So we know that there are 40 people in the universe, and we've got dark hair and brown eyes. Now, we know how many are in the dark hair. We know how many are in the brown eyes. And then we've been told that the union of those two sets is 26. Okay, so together these two sets here, or these three sets I should say, just dark hair and brown eyes, those three together end up being 26. But if you take the 23 people that have dark hair and add the 18 people that have brown eyes, I'm getting 41 people total. Now, so between this set and this set, I've got 41 people, but that means I've overlapped quite a few of them. And so what I got to do here is I got to figure out how many how many there are here that are over here. So 20, what have I got here? I had, sorry, 23 plus 18 gave me the 41. And I know that that should be 26, so that means I'm over by 15. So there are 15 people that are right there in that overlap between the two. And we've talked about that before, the way that overlap works. I'm glad that they gave us the union of the two sets here, because I don't know how many people are outside both of those sets. And so in a previous question, there was nobody outside those two sets, so I didn't have to worry about that. But here I do. Now, if there's 23 that have dark hair and 15 also have brown eyes, then there's going to be 8 that have dark hair and don't have brown eyes. If I've got 18 that have brown eyes and 15 of them have dark hair, then I know that there's going to be 3 that have brown eyes and don't have dark hair. Now, when you put those together, okay, bear in mind that we were told in here that we've got 26 people. And we do. If we add those numbers up we could get 26 people there. That means there's got to be 14 people outside of those two sets, so that the total of the universe here is going to be 40. So now, determine the probability that a child has, okay, dark hair and brown eyes. So probability that has dark hair and brown eyes. So that is going to be right in here. So 15 out of 40. Okay, and then we can simplify that. They're both divisible by 5, so 3 out of 8. How about neither dark hair nor brown eyes? So that's this group right out here. Okay, so that is dark hair union brown eyes. They don't have either one of those. Okay, don't have the dark hair, don't have the brown eyes, don't have both of them. So that's this bit out here. So it's going to be the 14 out of the 40. And those are both divisible by 2, so we're going to get 7 out of 20. Now over here, dark hair, probability of having dark hair, but not brown eyes. So dark hair and not brown eyes. So they're in the dark hair, okay, they're in the dark hair circle, but they don't have the brown, so they're not in the overlap. So it's just going to be that 8. Now, be careful here. That's just a random person that you're picking. You haven't specified a particular group. You're just looking at how many here, what's the probability that someone here has dark hair, but not the brown eyes there. Okay, that's going to be 8 out of 40, or 1/5 of the group. And now here it is, brown eyes, given that the child has dark hair. So this is brown eyes, given that the student or the child here has dark hair. So now what we're doing is we're looking very specifically at a certain set here. And we're only looking at this set of people here that have dark hair. There are 2 subsets there. So there are 15 out of that set. Okay, 15 out of that set that have brown eyes. And that total set there, when you add those together, we don't even have to add them together. You're told up here there's 23. So 15 out of 23. That's the probability that someone has brown eyes, given that, assuming that they've already got dark hair. Okay, so now for this question, we read that 50 students go bushwalking, 23 get sunburned, 22 get bitten by ants, and 5 are both sunburned and bitten by ants. It's a miserable little trip. Determine the probability of the randomly selected student, and we give the little options here, okay? So first of all, let's create our Venn diagram. We'll just kind of drop it right here. And then again, I'm going to put my little, off to the side here, that little number here, that's the size of the universe. There's 50. And so remember how this works here. I've got my 2 sets, and I have this one here is going to be sunburnt. This is going to be bitten by ants. Okay? And now we should be able to get through this a little bit quicker, because we've done enough of these that you very likely are seeing the pattern here. We're going to start with what's in the middle, that set that's shared between the 2 of them, and we see that 5 were both sunburnt and bitten by ants. So if 23 got sunburned, 23 are in this particular set here, and 5 are in that subset, then there's going to be 18 over here. And if there's 5 here and 22 in this particular subset, we know that there's going to be 17 over here. Now altogether, when we take a look at that, it's 18 plus 5 plus 17. That accounts for 40 people, which means if there's 50 here total, there's got to be 10 people that sit outside of the union of those 2 sets. So now determine the probability that a randomly selected student escaped being bitten. Okay, so the probability, and this is by ants, this is my ants here, so did not get bitten by ants. Okay, well, there were 22 there that got bitten by ants here. Now, in spite of the fact that I split that up, we are told that there were 22 that were bitten by ants here. So if you take the 22 away from the 50, that leaves us with 28 out of 50. And if we divide those both by 2, what do I got? I got 14 out of 25. Okay, so 14/25 is the probability that someone escaped being bitten. How about was either bitten or sunburned? Okay, so the probability that they're either bitten or sunburned here, that is, we're looking for the probability of being in the union of those two sets. Okay, because remember, or in this case is going to be this set, and including the overlap in between them. Now altogether we know that that's 40, okay, because we had just done that calculation there. That's 40 over 50, and that can be reduced to 4/5. Now, how about was neither bitten nor sunburned? Well, now that's the probability that you are not in the union of those two sets. And again, we've already dealt with that. There are 10 students that are out in that area here, and when you simplify that, it's a 1/5. Now, over here, what's the probability that the student was bitten given that the student was sunburned? So this is the probability that they were bitten by an ant given that they were sunburned. Okay, so we already know we're dealing with the sunburnt set of students. We're only looking at this group right here. There are 23 people here. There are 5 people that fall into the category of being bitten. So that's going to be 5 out of 23. Now, on the other hand, what's the probability that they were sunburnt given that the student was not bitten? Well, now that's a different sort of a question here. So given that they were not bitten, I want to know what's the probability that they were sunburned given that the student was not bitten? Well, not bitten is everything outside of this set. So what I'm going to do is I'm going to cover up the bitten set. And now what I've got here is this group here of 28 students, 18 in this subset, 10 in this subset here. So that's going to be, 28 students. I thought I said that wrong. Now, 18 of them, the smaller set here in this group is going to be this one right here, 18. And if you simplify that, let's divide them both by 2. I'm going to get 9 out of 14. So that's the probability that you were sunburnt given that you did not get bitten. Okay, hope that makes sense. Okay, so in this question, we read that 400 families were surveyed. It was found that 90% had a TV set and 60% had a computer. Now, I kind of have an idea where this question is going to go here, and we could work with just the 90% and the 60% and use those as our numbers here. But then at one point in the question, we're going to be building probabilities off of these kind of percentages, probabilities that we're given here. It might be easier just to say that if it's 90% at a TV, that's 360 people. And if 60% had a computer, that's 240, or I should say families, 360 families and 240 families. Okay? Now, we're given one extra little bit of information. Each family had at least one of those. Okay, so those two sets cover the whole universe. So let's take a quick look at this. And again, we've got 400 here in our universe. We've got our two sets. This was what? This was a TV, and this was a computer. Now, seeing as there's nothing in the outside here, there's nothing outside the union of those two sets here, let's just take a quick look here, because I'm given the information in the TV. I know that there's 360 there, and I know that there's 240 families here. But when you add those together, that looks like you're looking at 600 families. Well, that's 200 more than I know that I actually have here. But that's because I've counted this group here twice, which means if I'm over that limit, I've counted that overlap there has to be 200, okay? Because I've counted that 200 twice. Now let's push me over here. Now if that's 200, that means over here in the TV set, okay, there's 200 in the subset that include the computers, but there's got to be right now 160 out here that don't include the computer. For the computer, the families that have just the computer, there's going to be 40 out here that don't have the TV. And so altogether, you add those up, you're going to get the 400, and that's what we were told there, right? That the union of those two sets covers the whole thing. So now, if it's found that if one of these families is selected at random, find the probability that they have a TV, given that it has a computer. So given that it has a computer, it's going to be this set right here. We know that there's going to be 240 families in that set. And this is the subset that has the computer, so there's going to be 200 right there. Okay? So now what we're going to do here is we're just going to simplify the 240. I did it again. 200 over the 240. Okay, and they're both going to be, well, they're both divisible by 40, so it's going to be 5/6. Okay, and there you go. Okay, this next question is an interesting one here. The probability that Greta's mother takes her shopping is 2/5. Now, when Greta goes shopping with her mother, she gets an ice cream 70% of the time. When Greta does not go shopping with her, she gets an ice cream 30% of the time. So mom still buys her an ice cream 30% of the time. So determine the probability that Greta's mother buys her an ice cream when shopping. Okay, so what is the probability? Now, when we say went shopping here, we're talking about Greta's mother. Greta's mother goes out shopping. So what's the probability? Okay, the mother's going to go out. Now, we don't even, I'm not going to tell you whether or not Greta goes or not, because that's what we want to include in here. So basically, the probability that Greta gets an ice cream here, well, there's two distinct circumstances where that happens. One is where she goes shopping with her mother, and that changes the probability. The other one is when she doesn't. So what's the probability that Greta's mother takes her shopping? Well, that's 2/5. So 2/5 of the time Greta goes shopping. And when that happens, 70% of the time, okay, or 7 out of 10, 70% of the time she will get an ice cream. So that's one way that this could happen. Or she doesn't go get taken shopping, and that's going to be 3/5 of the time she doesn't go shopping with her mother. And when that happens, there's a 30% chance that she will get an ice cream. So that's going to be 3 out of 10. So probability that she goes shopping with her mom and gets an ice cream, or probability that she doesn't go shopping with her mom and gets an ice cream. Okay, so what have we got here? The denominator here is going to be 50. And then when we put our numerators together, that's going to be 2 times 7 is 14, 3 times 3 is 9, 14 and 9 is going to be 23. So 23 out of 50. That's the probability that Greta is going to get ice cream. Now let's take a look down here. What's the probability that Greta went shopping with her mother, given that her mother buys her ice cream? So what we've got here is what's the probability that she went shopping, given that she gets an ice cream? Now I haven't built myself a Venn diagram to look at this one through. And so maybe that's going to cause me a bit of a problem, but I do have a formula for this. And the formula is the probability that she goes shopping, S and I, divided by the probability of I. Now, in this particular problem, I have just figured out what the probability of I is. It's 23 out of 50. So now, what's the probability that she goes shopping and gets ice cream? Well, I had just done that one. That's this one going to be right here. That's going to be 2/5 multiplied by 7 over 10 by 70%. Now, I'm going to rewrite this down here just to illustrate a point here. So 2/5, 7 out of 10, plus 3/5, 3 out of 10. Okay. Please don't cancel those. Please don't cancel. They are the same. They look the same here. But because of the division line right here, there's an implied set of brackets here. I need to do this addition, okay, before I can do any kind of canceling there. So please don't do that. So we want to evaluate this. So this is now going to be 14 over 50 divided by, and what we already know is going to be 23 over 50. And when you simplify this expression by multiplying by the reciprocal, you're going to get 14 out of 23. So that's the probability that she went shopping, given that she has ice cream. So this, you kind of look at the scenario here. What's happening here is, let's say, the brother walks into the house and sees that Greta's got ice cream, and is now trying to figure out, well, what's the probability that she went shopping? Like, okay, he knows that she's got the ice cream. He just doesn't know whether or not she's gone shopping or not. Well, that's the probability. Okay, let's take a look at this question. Again, another interesting question here. On a given day, photocopier A has a 10% chance of a malfunction, and machine B has a 7% chance of the same thing, malfunction. So given that at least one of the machines has malfunctioned, what is the chance that it was B? So you think of the scenario like this. The technician's been called. The technician comes to let's say the school. walks in the door, and they already know, because they got called, they already know that at least one of the machines has gone down. So he's trying to figure out, well, what's the probability that it's going to be that B machine. So what we've got here is that's the probability of B given that at least one, okay, has occurred here. So now this is going to be the probability of B and at least one. We're going to talk about that in just a second here. And this is going to be the probability of at least one. Now, let's talk about this probability of at least one first. Probability of at least one here. Now, how does that work here? How are we going to figure that out here? Well, the thing is, we can assume, and it's a safe assumption here, that these machines are independent of each other. Okay? So that when one goes down, it doesn't affect whether or not the other one goes down here. So let's talk about A here. One way that this could occur here is that A could malfunction, but B doesn't. Or B malfunctions and A doesn't. Or they both malfunction. Okay, so I'm using the little bar here to just indicate that there was a problem. So what is the probability that A is a malfunction? It's going to be 10%. So that's going to be 0.1. And if B has a 7% chance of a malfunction, that means there's a 93% chance it doesn't. Then if A has a 10% chance of a malfunction, that means there's a 90% chance that it doesn't. And then B is going to be 0.07 that it malfunctions. And then over here, there's this slight chance that they both malfunction. Now let's evaluate that. So it's going to be 0.1 times 0.93 plus 0.9 times 0.07 plus 0.1 times 0.07. Put that all together and we get that this is going to be 0.163. Now, that's going to be our denominator here. Now, up here, it's the probability of B and at least one of those things going down. Okay? Well, B and at least one of them going down here, where they intersect here, they're going to intersect on these two terms. This is the one term here where at least one happens, but B breaking down doesn't happen. And what I'm looking for here is that, I probably should have been consistent up here if I'd gone like B breaks down. What's the probability that B breaks down together with at least one breaking down? So that's actually going to be these two terms together. So what that's going to be is it's going to be this point 0.9, 0.07, that's B breaking down, and A not breaking down. Or it could be that they both break down. Okay? Either way, B is part of that. And then we'll have this over the 0.163. So I'm going to put that into my calculator here. So 0.9 times 0.07 plus 0.1 times 0.07 divided by 0.163, and I get 0.429, that's one. So what we're looking at here, it's approximately a 43% chance that if at least one of them went down, it's B. Okay. So in this question, we read that a polygraph or lie detectors tests are generally not very accurate. Suppose that a polygraph is 70% accurate, and that is, if you lie, the polygraph indicates so 70% of the time, and if you tell the truth, it indicates so 70% of the time. Okay, so let's take a quick look at this. And actually, this is going to be fairly, it's going to hopefully give you some information, some insight as to how tests like this work. And now, the polygraph is one thing, but like this could be a medical test as well. This could be kind of any sort of a test for testing for something, right? Just kind of watch what happens here. So assume that the average person is truthful 90% of the time. So the vast majority of the time, we're being truthful, okay? So let's complete the following table. So 90% of the time, someone's going to be telling the truth, and 10% of the time they're going to be lying here. So now what happens here is if you're telling the truth, then what we know here is that 70% of the time the polygraph will indicate that you're telling the truth, which means 30% of the time it does that wrong. If you're lying, okay, then 30% of the time it's going to say that you're telling the truth, but 70% of that time it's going to tell you that you're lying, okay? So now we're going to figure out the probabilities here. So we got 0.9 times 0.7, that's going to be 0.63. So there we go. And then 0.9 times 0.3 is going to be 0.27. 0.1 times 0.3 is going to be 0.03. 0.1 times 0.7 is going to be 0.07. Okay? So here are the probabilities. Now, let's go on. So find the probability that an average person is telling the truth given that the polygraph test indicates that the truth. Now, this is the real question. Okay, so based on what we've just seen here about the accuracy of the polygraph here, now this is the question here. So what is the probability that you are actually telling the truth given that the polygraph says you're telling the truth? Because really that's what you're interested in, right? You've got someone strapped into this. It says you're telling the truth, but you can't trust it. Well, to what degree can you trust it? Well, this is going to be, the formula for this will be the probability that you're telling the truth and the polygraph says you're telling the truth over the probability that the polygraph says you're telling the truth. Well, let's look up here at our little chart here. So probability that you're telling the truth is up here and the polygraph says you're telling the truth is going to be 0.63. Now, but the polygraph saying that you're telling the truth, that could be either one of these branches right here. It could be the 0.063 or the 0.03. Okay? In both cases, the polygraph indicates you're telling the truth. So it's going to be 0.63 plus 0.03. Now let's evaluate that. 0.63 divided by 0.66. And we get that this is going to be 0.9545 and so on. So we're looking at approximately 95% of the time when the polygraph says that you're telling the truth, you're in fact telling the truth. Okay? Now let's look down here. On the other hand, what if you have a criminal? Oh, hold on a second. I want to just see something here. Okay. Assume that the criminals are truthful 15% of the time. Okay, so telling the truth here, 15% of the time. So that means 0.15, which means down here, it means 85% of the time they are lying. So 70%, 30%, 30%, 70%. Okay, so now let's multiply that out here. So 0.15 times 0.7. Okay, so that means 0.105. 0.15 times 0.3, 0.045. And then down here, now the probabilities are going to shift a little bit because the probability that the criminal is lying is quite high. 0.85 times 0.3, 0.255, and then 0.85 times 0.7, 0.595. Okay, now it's actually not part of this problem. Oh, I'm sorry, yes it is here, right here. Find the probability that the criminal is lying given that the polygraph indicates telling the truth. Now, so what we're looking for here is the probability, okay, the probability that the criminal is lying given that the polygraph indicates the truth. So that is going to be the probability of lying and the polygraph indicating it's the truth over the probability that the polygraph indicates the truth. So that is, so lying and indicating the truth is going to be 0.255 over, and once again, indicating the truth is the sum of those two. So 0.105 plus 0.255. And again, I'll just go to my calculator. Divided by plus 0.105. And we got 70, there we go. So this is going to be approximately 71% of the time. So roughly 71% of the time when the polygraph indicates that the person's telling, the criminal's telling the truth, actually they're lying. Okay, that's how we interpret that. Okay, so this question actually, we're going back a little bit. We're going to talk about expected value here shortly, but there's going to be a connection later on here. So bag A contains 2 red balls and 3 green balls. 2 balls are chosen at random from the bag without replacement. Let X denote the number of red balls chosen. The following table shows the probability distribution for X. Okay, so you're grabbing the 2 balls and you've got your probabilities sitting right there. Question is, calculate the expected value or the mean number of red balls chosen. And remember how that works here. So what we do is we simply take the result and multiply it by its corresponding probability. That's it. Okay. So 0 times 3/10 plus 1 times 3/5 plus 2 times 1/10. Now, putting that together, that's simply going to be 3/5 plus, well, when I put 2 times 1/10 is actually going to be 1/5. So the answer here is the probability, or not the probability, sorry, I should say that the expected value is 4/5. Meaning that after you do this sort of experiment kind of repeatedly, on average, you would expect to get 4/5 of a red ball, which I know sounds goofy, but when you look at the results over a long period of time and kind of divide out your results by the total number of attempts, that's what you would expect to get. Now this second part here says bag B contains 4 red balls, and 2 green balls. 2 balls are chosen at random from bag B without replacement. Now we're going to draw a tree diagram to represent that above information, including the probability. Okay, so here we go. So let's say this is going to be choosing the red, this will be choosing the green, and then this is going to split up again, and this will be, let's say, red, and this will be green, this will be red, and this will be green. So the probability that the first ball is red is going to be 4 out of 6. I'm going to leave it as 4 out of 6 because I think those numbers are going to be just a little bit easier to work with when I put it all together at the end here. So this is going to be 2 out of 6. Now, once I've done that, remember I'm not putting that ball back in, which means what's the probability that the next one is going to be red? Well, there's going to be 1 fewer, so there's going to be 3 out of 5. And for green, it's going to be 2 out of 5. Down here, if the first one I chose was green, the probability that the second one is going to be red is going to be 4 out of 5. And the probability that the second one's going to be green will be 1 out of 5. Now, let's multiply those together. Okay, so the probability that we're going to get the 2 reds here, that is going to be 12 out of 30. Okay, here this is going to be 8 out of 30. 2/6 times 4/5 is going to be 8 out of 30. And 2/6 times 1/5 is going to be 2 out of 30. Okay, and the nice thing here is, without simplifying here, I mean, I can tell right away that what we're going to get here is, okay, 12 and 8 is 20, and 8, 28 and 2 is 30. So add those all together and they add up to 1. Okay, so good. Now, so find the probability distribution of y, where y is the number of red balls chosen from bag B. So what's the probability that we chose no red? That's going to be 2 out of 30. And let's write that down now as simplified. Well, here we'll write it like this. 2 out of 30, which is going to be 1 out of 15. What's probably that you get 1 red? Well, 1 red is going to be either one of these. So I'm going to add those together. So it's going to be 16 out of 30. I divide those both by 2 and I get 8 out of 15. And the probability that I get 2 red balls, I should say, is going to be 12 out of 30. Okay, I divide those both by 6 and I'm going to get 2/5. Okay, now let's take a look at the last question here. Now that we've got these 2 different scenarios here, a standard die with 6 faces is rolled. If a 1 or a 6 is rolled, 2 balls are chosen from bag A. So we had to put the above 2 questions together. That's this one up here. These are the results from A. Okay. Otherwise, 2 balls are chosen from bag B. So what's the probability that 2 red balls are chosen? Okay. Okay, so probability of 2 red balls here. Well, okay. It could come from bag A. So that's going to be the probability of coming from bag A multiplied by the probability of getting 2 reds. Or it could be the probability of coming from bag B multiplied by the probability of 2 reds there. Okay, so now what's the probability that it comes from bag A? Well, if I roll a 1 or a 6 from bag A, well, that's going to be 2/6, okay, or 1/3. And the probability of 2 reds, well, we go back up to here. The probability of 2 reds is going to be 1/10. Or The probability that it comes from B is going to be 2/3. And the probability that I get 2 reds from, 2 reds from B is going to be 2/5. 2/5. Now, I'm kind of lazy here. I could put 2/5 here, but I'm actually going to put 4/10. Because in a second here, I'm going to add those together, and I might as well have common denominators. So that's going to be 1/30 plus 8/30, altogether 9/30. I can divide each of those by 3 to get 3/10. Okay, so the probability that I'm going to get 2 reds is going to be 30%, 3/10. Now, the last question here. Given that 2 red balls were obtained, so that's the result right here. Find the probability that a 1 or a 6 was rolled on the die. So really what that says here, what that's saying here is that it came from bag A. That's the kind of the sideways way of asking that. So the question is, what is the probability that it came from bag A, given that we had 2 reds that we pulled out here? So that is going to be the probability of coming from bag A and we get 2 reds, okay, over the probability of getting 2 reds. Now we've already just figured out the probability of 2 reds here. So the probability of getting it coming from bag A and getting 2 reds is going to be this right here. So that's going to be 1/3 multiplied by 1/10 over the sum of those two, which we've already figured out to be 3/10. So this is going to be 1/30 over 3/10. And when you multiply that around and well, I won't even bother canceling. We'll do it like this. This is going to be 10/90, so 1/9. The probability, so you're looking at the results, you see 2 reds. The probability that those 2 reds came from bag A is going to be 1/9.